For most of the 20th century, the icy moons of the outer planets were imagined as dead worlds, frozen relics, unchanged since the birth of the solar system, so far from the sun that any water they held must long ago have frozen solid to the core. At Jupiter, the sunlight is a mere 27th of what warms the Earth, at Neptune less than 1,000th. Surely, it seemed, these were nothing but inert balls of ice and rock. That picture has collapsed, over 3 decades of spacecraft reconnaissance, into one of the most consequential reframings in all of planetary science. We now know that beneath the frozen crusts of a whole family of these moons lie vast oceans of liquid water, global seas, tens of kilometers deep, holding in some cases several times the water of all the Earth's oceans combined. The moons once dismissed as iceballs are, we have learned, geologically and perhaps chemically alive. This chapter follows 5 of them, Europa, Enceladus, Ganymede, Titan and Triton, that anchor the new science of ocean worlds, and that have made the outer solar system the most promising place beyond Earth to search for life. An ocean world in the modern sense is a body that holds, or recently held, a layer of liquid water, most often a global sea sandwiched between an outer shell of ice and a rocky interior below. Since these oceans lie buried beneath kilometers of frozen crust, we cannot see them directly, and their discovery has depended on a handful of ingenious indirect signatures. A salty ocean conducts electricity, and when it is bathed in the changing magnetic field of its giant planet, that hidden conducting layer betrays itself by generating a magnetic field of its own, the telltale of Europa, Ganymede and Callisto. A moon whose icy shell floats free on a liquid layer will wobble as it spins a little, more than a solid one would, the telltale of Enceladus and Titan. Some worlds vent their oceans directly into space, where a passing spacecraft can catch the spray, and precise measures of a moon's gravity and shape can reveal a soft, low-density layer within. No one of these clues is decisive alone, which is why each world is judged on the agreement of several, and why real controversies persist where the evidence is still thin. What keeps these oceans from freezing, so far from the sun? The answer is heat generated from within, and above all the remarkable process of tidal heating. A moon on a slightly out-of-round orbit is squeezed and stretched by its planet's gravity as its distance rises and falls, and this endless flexing, like the working of a wire bent back and forth, dissipates energy as heat deep in the moon's body. The crucial point is that the heating depends on the orbit being eccentric, on it not being a perfect circle, yet tides themselves tend to round an orbit off over time, so a lasting ocean needs something to keep the orbit eccentric, and that something is orbital resonance. The 3 inner large moons of Jupiter, Io, Europa and Ganymede are locked in a clockwork discovered by Laplace 2 centuries ago. For every 4 orbits of Io, Europa completes 2 and Ganymede 1. Trapped in this rhythm, the moons tug on one another and force each other's orbits to stay slightly elliptical, and it is that forced ellipticity which powers the heating that keeps their oceans liquid. At Saturn, a similar resonance between Enceladus and Dione does the same. The power of this process is written most vividly on Io, the innermost of the large Jovian moons, which sits closest to Jupiter and is flexed hardest of all. Io is the most volcanically active body in the solar system, its surface a hellscape of hundreds of erupting volcanoes and vast lakes of lava, pouring out more than 20 times the internal heat of the entire Earth. It is so fiercely heated that it has no ocean at all. Whatever water it once held was cooked away long ago, leaving a dry, silicate world over a possible sea of molten rock. Io is the cautionary bookend of the ocean world story, the very same resonance that keeps Europa's and Ganymede's water liquid would, turned up just a little, boil it away entirely. The habitable icy moons occupy a narrow, Goldilocks band of tidal heating, enough to melt the ice and keep a sea, but not so much as to drive off the volatiles. Ocean worlds exist because their moons are warmed just right, neither frozen dead like the distant iceballs, nor scorched dry like Io. Europa, the smallest of Jupiter's 4 great moons, is the benchmark ocean world, a body a little smaller than our own moon, wrapped in a shell of water ice, beneath which lies a global ocean thought to hold more water than all the seas of Earth. The strongest evidence for that ocean is magnetic, and it came from NASA Galileo orbiter in the 1990s. Jupiter's magnetic field is tilted from its spin axis, so the field sweeping over Europa rises and falls as the giant planet turns. A buried layer of salty, conducting water would respond to that changing field by generating a magnetic field of its own, opposing the change. And this is exactly what Galileo detected, an induced field of nearly the full strength expected from a near-surface conducting shell. Pure ice is far too poor a conductor to do it. Only a global layer of salty liquid water fits the measurement. The same technique, refined, is the very method by which the newly launched Europa Clipper will pin down how deep and how salty that ocean is. Europa's surface tells the same story in a different language. It is among the smoothest and youngest faces in the solar system, so lightly cratered that it can be no more than a few tens of millions of years old, far younger than the Moon itself, which means it is being continually resurfaced from within. It is laced with long cracks thought to open under tidal stress and scarred with chaos terrain, regions where the icy crust seems to have shattered into rafts that foundered and refroze, exactly as one would expect of a shell floating on liquid water below. Just how thick that shell is has been long debated, but a recent reading from the Juno spacecraft points to an average of about 29 kilometers of ice in the region it surveyed, a shell that thick makes the direct exchange of material between ocean and surface harder, which matters for life, because Europa's promise is that oxidizing chemicals forged by Jupiter's fierce radiation on its icy surface might sink to meet hydrogen welling up from the rock below, setting up the kind of chemical battery that life could feed upon. Whether Europa also vents plumes of water into space, as some tantalizing but unconfirmed observations suggest, remains an open question. If Europa is the benchmark, tiny Enceladus is the revelation, for it does something no other ocean world is known to do. It sprays its ocean into space, where a spacecraft has flown through the spray and tasted it directly. Enceladus is small enough to fit within the length of Britain, and for most of history it seemed an unremarkable snowball. Then, in 2005, the Cassini orbiter discovered a towering plume of water vapor and ice grains jetting hundreds of kilometers into space from 4 warm fractures across the Moon's south pole, the tiger stripes that glow with internal heat. Here was an ocean world caught in the act of venting, and over the years that followed, Cassini flew again and again straight through the plume, its instruments sampling the material as it passed. No drilling, no landing, the Moon simply handed its ocean up to be read. It was, and remains, the most productive encounter in the whole science of ocean worlds, the one place where we have held a piece of an alien sea in our instruments and asked it what it was made of. That the plume draws on a global ocean and not merely a local pocket of melt was proved by a beautifully subtle measurement: the Moon's libration, the slight rocking of its rotation. A Moon frozen solid all the way through would rock by a small, calculable amount as it orbits. Cassini measured Enceladus rocking by rather more than that, too much for a solid body, and just right for one whose icy shell is floating free, detached from the rocky core beneath by a global layer of liquid water. Together with the Moon's gravity and its shape, the wobble pins down an ocean tens of kilometers deep, wrapped around the whole Moon beneath an ice shell that thins toward the South Pole where the plume breaks through. That, a body barely 500 kilometers across, a fraction the size of our Moon, should hold a warm, global, actively vented sea is astonishing, and it forced planetary scientists to accept that even the smallest icy moons could be alive within, and what a sea it turned out to be. The plume's composition reads like a checklist for life. It is almost all water vapor, but laced through it Cassini found molecular hydrogen, and hydrogen in that setting is the signature of hot water reacting with rock at the ocean floor, the same chemistry that feeds some of the most ancient microbes on Earth. It found tiny grains of silica that can only form in water hotter than about 90 degrees, betraying active hydrothermal vents on the seabed. From the salts frozen into the ice grains, it reconstructed the ocean itself, a salty, alkaline, carbonate-rich brine, in lasting contact with rock. And in the last few years, reanalysis of Cassini's data has turned up 2 more prizes: phosphorus, the rarest of the elements life requires, at concentrations far above those in Earth's seas, and hydrogen cyanide, a versatile building block for the chemistry that precedes life. Enceladus is now known to possess liquid water, a source of chemical energy, and every one of the elements life is built from, the most complete inventory of habitability anywhere beyond the Earth. The great caveat always is that to be habitable is not to be inhabited. One large question hangs over this hopeful picture: how long has it lasted? A Moon as small as Enceladus should, left to itself, freeze its ocean solid within a few tens of millions of years, unless it is constantly reheated, and its heating depends on the resonance with Dione that keeps its orbit eccentric, a resonance that may itself be young, or may switch on and off over time. So the present vigorous activity might be a steady condition 4.5 billion years old, or it might be a recent and passing phase. The difference matters enormously for the prospects of life, for a biosphere needs time to arise, and an ocean that has only lately thawed, or that freezes and melts in fits and starts, is a far less promising cradle than one that has simmered, warm and chemically rich, since the dawn of the solar system. Whether Enceladus's ocean is ancient and enduring or young and episodic is unresolved, and it is one of the sharpest questions a future mission to the moon would be sent to answer. Titan, Saturn's giant moon and the second largest in the solar system, is an ocean world of a wholly different and stranger kind, for it has not one habitat but two. It is the only moon with a thick atmosphere, a dense veil of nitrogen half again as heavy as the Earth's air at sea level, tinted orange by a smog of complex organic molecules, and beneath that haze lies the only world besides Earth known to have stable liquid on its surface, not water, which is frozen rock-hard at Titan's temperature of nearly -180 degrees, but liquid methane and ethane, pooled into great polar seas fed by rivers and rain. The Cassini mission mapped these hydrocarbon seas by radar, and its Huygens probe parachuted down through the haze in 2005 to land on a damp, pebble-strewn shore, the most distant landing humanity has ever made. On Titan, methane plays the part that water plays on Earth, cycling between sky and sea, while sunlight and Saturn's radiation brew the air into ever more complex organics that rain down and gather, a planet-sized laboratory for the chemistry that may have preceded life on the young Earth. Beneath that exotic surface, Titan was long believed to hide a second habitat, a deep internal ocean of water mixed with ammonia, buried perhaps 50 to 100 kilometers down, inferred from the moon's gravity and the tilt and tides Cassini measured. That made Titan a two-in-one world, a frigid organic surface over a hidden water sea. But here the chapter must flag a live scientific dispute, of the kind that keeps even settled-seeming facts honest. A very recent reanalysis of Cassini's data has argued that Titan's interior dissipates tidal energy far more strongly than a body with a buried ocean should, and since a liquid layer would cushion that dissipation, the authors contend the measurements point instead to an oceanless interior, one that can still reproduce the older evidence. This is a single, recent, contested result, not a new consensus, and the long-standing case for Titan's ocean has not been abandoned. But it is a useful reminder that in a science built on sparse data from distant worlds, even a fact thought firm can be reopened by a sharper look. What is not in doubt is Titan's value as a target, which is why a nuclear-powered rotorcraft is being sent to fly across it. Ganymede is the giant of moons, the largest in the whole solar system, bigger even than the planet Mercury, and the outermost of Jupiter's 3 resonant moons. It is unique among moons in one spectacular respect. It generates its own magnetic field from a churning dynamo in a molten iron core, the only moon known to do so, and that field carves out a small magnetic bubble within Jupiter's vast one, kindling auroras over Ganymede's poles. And it was those auroras that revealed its ocean. Watching them with the Hubble telescope, astronomers saw the glowing ovals rock back and forth as Jupiter's field oscillated, but rock far less than they should have, had the moon been solid throughout. Something beneath the surface was pushing back, a salty, conducting ocean generating its own opposing field and damping the aurora's sway. The ocean it revealed is staggering, perhaps 100 kilometers deep, holding more water than all the surface water of Earth, but buried beneath a shell of ice some 150 kilometers thick. Yet Ganymede's vast ocean is, on present understanding, a less hopeful place for life than the smaller seas of Europa and Enceladus, and the reason lies in its very size. Ganymede is so large that the pressure at the bottom of its water layer is immense, great, enough to freeze water into exotic, dense forms of ice even while it stays warm. Its ocean is therefore likely trapped between 2 layers of ice, ordinary ice above, and high-pressure ice below, rather than resting directly on rock as Europa's and Enceladus's seas do. And that matters because it is the contact between water and rock that supplies the chemical nutrients and energy on which a chemosynthetic life would feed. An ocean sealed away from the rock, floating between icy floors, is enormous but chemically starved. Ganymede's ancient, cratered surface, meanwhile, carries the scar of a colossal early impact, a vast system of concentric furrows whose center suggests the whole moon was tipped over and reoriented by the blow. It is the prime destination of Europe's JUICE mission, which will become the first spacecraft ever to orbit a moon other than our own. Triton, the largest moon of Neptune, is the odd one out of this chapter, and one of the most intriguing worlds in the solar system. Its orbit gives it away. Triton circles Neptune backwards, against the planet's spin on a steeply tilted path, an orbit no moon born alongside its planet could have. Triton, the evidence overwhelmingly says, was not born at Neptune at all, but captured, a wanderer from the Kuiper-belt beyond, a frozen dwarf world cousin of Pluto, seized by Neptune's gravity in the distant past. And that violent capture has consequences, for circularizing Triton's original wild orbit would have flexed and heated the moon enormously, very likely melting much of its interior, perhaps creating, and perhaps still sustaining, a subsurface ocean beneath its crust. Triton thus stretches the idea of an ocean world outward to the very edge of the planetary system, and to the vast population of icy bodies from which it was stolen. The one spacecraft ever to see Triton up close, Voyager 2, swept past in 1989 and found not a dead husk but a startlingly young and active world. Its surface, dimpled into a strange cantaloupe texture found nowhere else, bears so few craters that it can be only tens of millions of years old, being constantly repaved. It is fabulously cold, just 38 degrees above absolute zero, among the coldest surfaces ever measured, wrapped in the thinnest wisp of nitrogen air. And most wonderful of all, Voyager caught Triton erupting, plumes of nitrogen gas and dark dust shooting 8 kilometers into the sky and streaming 100 kilometers downwind. The favored explanation is a kind of solar engine. Sunlight filtering through the clear surface ice warms a dark layer a little way beneath, until trapped nitrogen flashes to gas and bursts upward through the crust, carrying dust aloft. Whether these geysers connect to a deep interior ocean or are only a shallow, seasonal breath of the surface, no one yet knows, for Triton has been visited only that once briefly, more than 30 years ago, and awaits its next explorer still. The whole science of ocean worlds was built, world by world, on a handful of robotic emissaries. The two Voyagers in the 1970s and 80s gave humanity its first close looks at the moons of Jupiter, Saturn and Neptune, and caught Triton's plumes. Galileo, orbiting Jupiter through the turn of the century, gathered the magnetic evidence for oceans at Europa, Ganymede and Callisto, and found Ganymede's dynamo. And Cassini, orbiting Saturn for 13 years, became the defining ocean world's mission of all, discovering and repeatedly flying through the Enceladus plume, sampling an alien sea, and landing a probe on Titan. Each of these was, at heart, a mission of reconnaissance, answering the first great question, is there liquid water out there, with an emphatic and repeated yes. The task of the next generation is harder, not merely to find the oceans, but to weigh their fitness for life, and in time to look for life itself. 3 missions now carry that task forward. The first is Europa Clipper, launched in October 2024, the largest spacecraft NASA has ever built for a planetary mission. It will not orbit Europa directly, for the radiation there is lethal. Instead, it will loop around Jupiter and swing past Europa nearly 50 times, some passes skimming just 25 kilometers above the ice. Its instruments, cameras and spectrometers, a magnetometer, a dust and plasma analyzer, and an ice-penetrating radar designed to see right through the shell to the ocean below, are built to confirm and measure that ocean, to gauge how thick the ice is and how salty the water, and to judge whether Europa is truly fit for life. It is important to be clear about its purpose. Europa Clipper is not a life detection mission. It is a reconnaissance of habitability, sent to ask whether the conditions for life are present, not yet whether life itself is there. It will reach Jupiter in 2030, after a long looping cruise past Mars and back by the Earth, and begin the closest study of an ocean world ever attempted. 2 more are on their way. Europe's JUICE spacecraft, launched in 2023, will reach Jupiter in the early 2030s, and after touring Europa, Ganymede and Callisto, will settle into orbit around Ganymede itself, the first time any craft has orbited a moon other than our own, to study its ocean, its magnetic field and its dynamo in unprecedented detail. And NASA Dragonfly, a nuclear-powered rotorcraft the size of a small car, will do something stranger still. It will fly on Titan, hopping from site to site across the dunes and craters of that organic world on 8 whirling rotors, borne up by the thick cold air. Launching later this decade and arriving in the mid-30s, Dragonfly will sample Titan's probiotic chemistry directly and search for the chemical hints of biology, though, like Clipper, it is designed to study the chemistry that comes before life, not to catch life in the act. Beyond these three, a return to Enceladus to fly its plume with sharper instruments and a mission back to Neptune and Triton stand high on the wish lists of planetary scientists, still awaiting their turn. What would it take for one of these oceans to be not merely habitable but inhabited? Planetary scientists apply a consistent triad: liquid water as a solvent. The handful of elements life is built from: carbon, hydrogen, nitrogen, oxygen, phosphorus and sulfur, and a source of chemical energy some imbalance or metabolism could exploit. Sunlight, the energy of Earth's surface life, is absent beneath kilometers of ice, so any life in these buried seas must live as the strange communities around Earth's deep-sea vents do, feeding not on light but on chemistry, in total darkness. Enceladus, remarkably, is now known to offer all three at once: water, every one of the essential elements, and a hydrothermal chemistry pouring out usable energy. Europa offers a different architecture, a vast sea where oxidants made on the surface by radiation might sink to meet hydrogen rising from the rock, a battery of chemical opposites across the shell. Ganymede's and Titan's water oceans, sealed between layers of ice, are less obviously promising, and Titan's methane surface raises the wilder, wholly unproven possibility of a life that might use liquid methane, rather than water, as its solvent. Finding life, if it is there, will be far harder than finding the oceans that might hold it, for the hardest problem of all is telling a true sign of biology from a chemical mimic. The lifeless chemistry of rock and water and radiation can itself produce organic molecules, methane, even the building blocks of amino acids, and any candidate biosignature must be weighed against that abiotic background with the greatest care. Robust proof of life will demand several independent lines of evidence at once: patterns in the molecules that biology makes, and chemistry does not easily counterfeit, read against a well-understood baseline of what the non-living world can do. That is precisely why the missions of this decade are cast as scouts of habitability rather than hunters of life. They must first map the chemistry of the possible before the search for the actual can begin, and yet the shift already accomplished is profound. A single lifetime ago, the outer moons were frozen afterthoughts. Today we know their hidden oceans hold more water than all the seas of Earth, warmed from within and stirred with the ingredients of life. The old question, is there liquid water out there, has been answered abundantly: yes. The new one, is any of it alive, is the question the coming age of exploration was built for the first time to ask.